Hello, and welcome to the live stream of an Electron launch. This time it's going to be two satellites, Black Sky satellites, 16 and 17. My name's Josiah, and I'm a space engineer. I go to the University of Bremen, and I'm also the chief engineer of a rocketry group that is focused on building a rocket that goes to the Kármán line. So it's always interesting to see what's going on in the professional industry for how rockets are designed and what maybe the high technologies are of the in the sector, and maybe we can gain some ideas about how we want to build our rockets by looking at what the professionals are doing. So yeah, without getting too into the details, we're about 17 minutes away from the launch here, so we're going to be switching over to the Electron live stream. So yeah, these live streams that I do are pretty not too intense. We just like to sit around and talk about the satellites and the rockets and some of the interesting details about how the rockets are engineered and designed. And if you have any questions along the way, feel free to put it in the chat and maybe we can talk about it. So yeah, let's get into it.
From Mission Control to show you how it's done.
So
Powered by
yeah, we have
artificial intelligence, Black Sky
Electron
can use its
vehicle here sitting on the
constellation to
pad.
monitor activities and locations around the world. This provides valuable insights to decision makers across government, commercial, and humanitarian aid.
It looks like filling's underway here, so yeah, it's going to be about 15 more minutes until we get into the actual launch of the rocket. So let's go into a little bit about what is being launched on this vehicle. So one big thing here that's the satellite that's going to be going on this vehicle is called Black Sky. And this is actually a really interesting constellation because it is, in the end, going to be a constellation of 60 satellites that are going to be performing Earth observation. And basically what we have here is, it's essentially just a telescope with kind of a box underneath it. I don't know if you can kind of tell from this perspective, but the silver part in the middle there is the telescope part. And essentially it's just a telescope that points at Earth, and you can do Earth observation with this in the visible spectrum. And this is obviously gaining a lot of really interesting data. It has a resolution of 1 pixel is equal to 1 meter, which is pretty impressive when you think that it's like orbiting 500 kilometers above the Earth. So it can see like really, really well. It's not quite good enough that it could like resolve a person, but you could definitely resolve a lot of cool things with this type of a telescope. And yeah, the satellites that are going up are the 16th and 17th ones, or the numbers are 16 and 17. They don't actually have 15 satellites in orbit already, though. They had some failures initially, and they also have some satellites that have not launched yet that are in the earlier numbers. So if we remember back a couple years ago, Electron actually had a vehicle failure and was actually also carrying some of these Black Sky satellites in that case. So it's not the number that the satellite is not corresponding directly to how many are in orbit. Right now there's 12 that are operational. So yeah, once they have the full constellation, though, this will actually be one of the most effective Earth observation constellations. One of the key things that's important for Earth observation is that you keep coming over the same spot repeatedly, so that you can see changes of an area over time. Obviously, that's kind of the whole point of Earth observation. So this constellation actually has the highest rate of reflight over each area, just because they have so many of these telescopes that are orbiting. So it'll be interesting to see how the commercial sector reacts to this kind of a disruptive constellation, I would say. I don't think it has more reflight frequency than some of maybe the American spy satellites, but we don't really know the numbers on that. So at least for the commercially, it's one of the best. Another interesting thing about the Black Sky satellites is that they use this water thruster in order to generate thrust for the vehicle and keep it in orbit. And that's not usually typical, I would say, of current satellites. Usually they're using an electric propulsion or compressed nitrous oxide, or they also sometimes use hypergolic propellants. So this is somewhat of an uncommon solution. It doesn't really have that high of an efficiency using water, but obviously it's really simple because you just have water basically that is in this tank part on the right-hand side of this picture, and then you have a heater that's on the edge of that, and then the water goes through. It gets superheated to like a couple hundred degrees Celsius, and then that steam gets shot out the back of the thruster, and that's what generates the thrust. So it's really simple. You just basically need an electric heater and some water, and then boom, you got a thruster. Unfortunately, that means that the satellite's not going to survive very long, so it'll run out of this water propellant after only 3 years, and then essentially the satellite will deorbit at that point. This means that Black Sky plans to operate the satellite constellation in a way that they're going to be replacing these satellites on a continuous basis. So it's going to create a lot of a market for launching these satellites, obviously, if they have to replace 60 satellites every 3 years. So I guess good for the launch vehicle. All right, let's head back to the mainstream and see what's going on. So yeah, propellant loading looks like it's still happening here. Those clouds that are coming off the vehicle are basically indicating that they're loading up the liquid oxygen into the vehicle. That's the oxidizer that the vehicle uses in order to generate thrust, of course. And you can kind of tell where the propellant tanks are because, of course, it's white where the liquid oxygen is sitting, and that's just because the liquid oxygen is so cold that it's causing water in the air to condense onto the rocket vehicle and freeze. So it's like ice, basically, that's sticking onto the vehicle. So yeah, of course it's using liquid oxygen and RP1, which is basically a refined kerosene, in order to power its engines for the first stage and the second stage. And you can kind of see the divisions between the stages just by looking at where that ice is. But yeah, let's switch back to the audio that they have.
GC, LD on mission.
LD, GC.
Yes, sir. Please proceed with sequence 55, the pad terminal checks.
Sequence 55 in work.
Now, before we get into a little more detail about Electron, for those who might have missed our launch last month, we lifted off from Pad B here at Launch Complex 1 for the very first time. This is our third pad globally, allowing us to launch and then launch again without the hindrance of pad maintenance or recycle time. Pad B joins Pad A, which we're launching from today, at LC-1 in Mahia, the world's first private orbital launch site on the east coast of New Zealand. At Launch Complex 1, we're capable of supporting up to 120 launch opportunities every year. Now, unfortunately, we won't be launching Neutron from either of these pads. We'll be launching Neutron from Rocketlab's Launch Complex 2 on Wallops Island in Virginia. Neutron is the program that Alex here works on, and it sounds like you're looking for colleagues.
That's right, and we're looking to expand the team fast. We've got roles in propulsion, vehicle design, analysis, and plenty more. So if you're interested in building the rocket of 2050 today, check out the careers page on our website at rocketlabusa.com. And if you haven't seen it yet, here's a sneak peek of what our new 250,000 square foot facility will look like. This building will facilitate rocket production, assembly, and integration, and will be home to our 5th Global Operations Centre for launch and on-orbit operations. Plus, we'll be launching and landing Neutron just down the road at the southern end of Wallops Island.
Sounds like that they're interested in doing some recruiting as well. So keep that in mind, all you rocket engineers out there in America. There's all kinds of companies like Rocketlab that are looking to have new people joining aboard. If you're international, unfortunately, Rocketlab doesn't hire people who are international because of issues with ITAR restrictions. But that's just one unfortunate thing, I guess. But there are some companies that are European and from other places in the world that are still hiring, so not to worry. They mentioned that they're launching their rocket from New Zealand, and basically they have this one launch site in New Zealand, and they also have another one that's in Virginia. The advantage of having the one in New Zealand is basically they're on this peninsula that overlooks water everywhere. So basically they can launch in any orientation. Like if they go east, they can go south. They can't go west because that goes over the other side of New Zealand, but they can go pretty much any other direction, and they can really optimize how they can design their trajectories because of that launch location. So it's really nice. And we did a video a month or two ago about where to best launch rockets, and it kind of goes over that kind of stuff.
The liquid oxygen and kerosene propellant mix is used to power the 9 3D printed Rutherford engines on stage 1. These engines are named after Sir Ernest Rutherford, the famous physicist and New Zealander who discovered the radioactive element radon, as well as the concept of radioactive half-life.
That's right. Those 9 Rutherford engines power the first stage until Electron is at an altitude of around 70 kilometers above sea level. At this point, the next stage of the journey is carried by just one Rutherford engine, specially designed to work in the vacuum of space. We also have another engine named after another famous physicist, Marie Curie. Our Curie engine is the 11th engine on Electron and is housed within Electron's third stage, also known as the kick stage. This kick stage is important for delivering the payload to its exact destination in space. Today, after Electron lifts off the pad and successfully completes stage 1 and stage 2 burn to get us into space, Curie will then kick in to propel Black Sky's 2 satellites to a 430-kilometer circular orbit.
The kick stage is a small but mighty upper stage responsible for our incredibly accurate payload insertion, on average within just 1 kilometre of the target orbit. In order to achieve this high accuracy, we separate the kick stage just at the perigee of orbit as shown here. Today, satellites are headed to a circular orbit, but when we first separate the kick stage, it's on an elliptical first pass. It needs a propulsion system to boost it up into the right orbit for payload deployment, and that's where Curie comes in.
So we enter a coast phase for a period of time until the kick stage and attached payloads reach their desired apogee. That's when the Mark II Curie engine ignites for about 45 seconds to circularize the orbit ahead of payload deployment shortly after. From here, our Curie engine can reignite to lower the apogee, reducing the on-orbit time by up to 99.7%, doing our part to keep space nice and tidy.
Now, while we are best known for our rockets, we also make spacecraft components used.
So they just mentioned a little bit about how their rocket is working, specifically talking about the Madame Curie upper stage, which is actually a really cool part of how Rocketlab operates. I'm just going to switch over to a diagram that I have of the vehicle. So basically you can see here how the vehicle is broken down. On the bottom here we have the first stage, which is comprising most of the vehicle. And down there they have the 9 Rutherford engines that they utilize to power that first stage. And then at the very top here we have the second stage, and then on the nose cone here on the top is where the payload goes. And in this case they have this Madame Curie upper stage, which attaches kind of to that payload section, and that acts as kind of a third stage or a kick stage. And that allows them to do that circularization maneuver that they were talking about in the diagram. So that's a bit interesting. Another part about the Electron rocket that's interesting is that it uses electric-driven pumps. So usually for rockets, it would look kind of similar to the one on the left, where basically we have fuel and oxidizer that flow into a pre-burner. That's the yellow part here. And that essentially powers a turbine, which is the black circle here. And that turbine is what spins the pumps. So it's kind of like this situation where we're using a little bit of fuel to power the pumps that push the fuel into the combustion chamber. Because of course we need to have the fuel and oxidizer at a high pressure in order to push them into the combustion chamber so that they don't start flowing backwards, and that will cause an explosion. So this is what's interesting though is that instead of doing that, the Electron is going to use basically an electric pump. So it's using electricity to power the pump, and then you don't have to waste fuel to power your rocket. And it's also a lot simpler because turbines are really complicated, and connecting them with pumps and having them all synced up is kind of a real challenge. So by using this electric pump, they're really simplifying the system a lot. And this is also another thing that causes them to design their vehicle more cheaply and to design it so that you can build it really quickly, which is another feature that comes with Electron. So we're getting close to launch here. I think we're within a minute. So the key things to look out for are going to be when it goes through max Q, which is going to be after only about 30 or 40 seconds into the launch. Then it's going to separate the first stage after about 2.5 minutes. So the first stage is going to accelerate. First stage will accelerate the vehicle about a quarter of the way to orbit, and then it's going to separate, and the second stage is going to kick off and do the rest of the work.
Ox load complete. Skate in recirc.
So it looks like everything's green right now. No problems.
AFTS is green and enabled for flight. Anti-geysering disabled.
It's really cool to see the ice on the vehicle in the nighttime like this. It really makes it quite shiny. The vehicle's actually completely black, so like you can really tell how much ice is on the vehicle.
Stage 1 and Stage 2 are pressed for flight.
High flow
I
engine.
bet that
purge
probably
enabled.
affects their performance.
What
The
did
thing with the
Dowie just
Electron is that
activate?
it's built completely out of carbon fiber, so the walls are so thin that basically you have just like 2 or 3 millimeters that are separating this liquid oxygen
T-minus
from
20 seconds
the
and
air,
counting.
essentially.
Ten, 9, 8, 7, 6, 5, 4, 3, 2.
All right, here we go. That's liftoff.
We have liftoff.
Stage 1 propulsion is nominal.
HV battery discharge is nominal.
Wow, it's looking quite brilliant. There we go. That's the view we want to see.
And there we have it. Our 25th Electron launch vehicle is off the pad for this mission and progressing well on its way to low Earth orbit. Soon the vehicle will approach the point in its journey when it experiences the most amount of stress, maximum aerodynamic
So it's gonna
pressure,
be going
which
through
is
max
known
Q
as
here.
max Q.
So we should be seeing the first stage separation coming up in just a
And there we
minute and a
have
half
it. We
or
have
so.
word from Mission Control that we can confirm that Electron has successfully passed through max Q and is continuing on its southeastern trajectory off the coast of New Zealand. The first stage's Rutherford engines are firing perfectly as we come up to the next major milestone ahead of the first separation event for Electron.
And you see how
Check-in
the
station.
plumes of the rocket are kind of expanding like a flower? That's because the atmosphere is getting thinner and thinner as the rocket goes higher and higher.
We're approaching main engine cutoff, or MECO.
And that
This is
essentially
when
means
Electron
that
throttles
the
down
pressure
just
that's
a
in
bit
the
before
gas as it
shutting
goes
off
out of
those
the nozzle
9 Rutherford engines on
is
stage
causing
1
it to expand
we
more and
mentioned
more.
earlier. This reduction in thrust allows for a clean separation of the first and second stages before the singular Rutherford engine on the second stage fires up and takes the satellites the rest of the way into orbit. We should see both of those actions on screen and hear the call-outs from our operators and mission control shortly.
Okay, here we go. It should be coming up just now.
MECO confirmed.
Yeah. Oh, wow.
Stage separation confirmed.
You know, watching the engine plumes in the night is
Stage 2
just
ignition.
spectacular.
There we go. We have confirmed a successful transition from the first to second stages of Electron's
And just
flight,
to remind you that
with MECO,
they'll not be
stage
recovering
separation
the...
and second stage ignition all nominal. You can now see the orange glow of the space-optimized
HV
Rutherford
battery
engine as it carries on
discharge.
into space.
The protective shell at the top of Electron, known as the payload fairing, protects the satellites as the vehicle launches through Earth's atmosphere. Since we've now cleared the lower atmosphere, those satellites don't need that protection anymore. In fact, we need to jettison that protective
Fairing
shell
separation
so we can
confirmed.
safely deploy the satellites to low Earth orbit.
Bottom holding nominal.
There goes the payload fairing. Black Sky's satellites are now
Guidance
exposed to space, no longer needing this shell to protect them, as Electron has already punched through Earth's atmosphere to take them to their orbital destination. We've got a short time gap now between this latest event and the next one coming up for Electron's second stage, which involves swapping out the batteries that power the second stage Rutherford engine. The mission is continuing nominally as we approach that next milestone, with the second stage traveling at nearly 9,000 kilometers an hour at an altitude of 139 kilometers.
So they just mentioned a little bit about the battery hot swap that they mentioned, and this is basically what's going to happen is that because the upper stage is powered by this electric pump, it needs obviously some big batteries to energize that. So what they're going to do is they're going to basically jettison part of the battery pack that doesn't have any charge anymore, so they can reduce the weight of the vehicle as they continue to orbit.
They'll join the rest of Black Sky's constellation of Earth-observing smallsats.
Yeah, if they didn't do that battery hot swap, then they would basically be taking a bunch of dead batteries to orbit, and that's, I guess, not really a useful strategy. So this is why they do it this way. And yeah, just to remind you again, they're not going to recover the first stage of the launch vehicle. So they're still working on developing recovery for that first stage. So that's something that will come in a later mission, but not on this one.
It travels at nearly 12,000 kilometers per hour.
And I think the piece there on the right that's kind of like sticking out beside the nozzle, I think that's actually part of the battery pack. So I think that's the part that's going to fly off, if I'm not mistaken.
Back to the mission on your screen, we're coming up to a milestone you'll see used only on Electron, the swap out of batteries that our Rutherford engines draw their energy from to continue operating their pumps. The vehicle has run through the set of batteries we started with at stage separation, and so now the second stage of the vehicle needs to swap over to a fresh battery to keep things going. We call this move the battery hot swap. We should hear that call come from mission control shortly, but keep an eye on your screen too, as sometimes you can catch a glimpse of them falling away.
Seconds remaining.
HV battery discharge nominal. Approaching hot swap.
All right, the battery should be coming off pretty soon here.
Starting throttle down.
Maybe you can't. Maybe we can't see it when we're in the dark like this. Oh, there it went. Did it just go? It just went. It was like one frame, then it was gone.
Battery Jason.
Wow. Okay.
And there goes the call for a successful battery hot swap. You've seen the shiny silver object on your screen falling away from the second stage engine. Electron continues well onto its target
Okay,
430
yes, it's
kilometers orbit, traveling at a speed of 16,000 kilometers per hour and an altitude of 200 kilometers.
They should call that like battery ejection. It was like there and then it was gone. My goodness. Okay, so it has another couple of minutes here to the final orbit that it's going to go into, and then the second stage is going to separate, and then the Madame Curie upper stage is going to take over.
Electron is currently in its
after,
second stage burn on the way to low Earth orbit to deliver Black Sky's payloads. We know that Black Sky's constellation can be used by all sorts of groups and
Stage two
organizations
propulsion
between
holding up.
government, commercial, and aid. But what does that actually look like on the ground? To give you some idea, Black Sky's AI-powered constellation was recently used to evaluate the impact of the COVID-19 pandemic on shipping and supply chain logistics around the world.
Yes, Astra Bremen is from Germany, indeed. Bremen is a city in Germany that's actually about 100 kilometers away from Hamburg. So, yeah, we're a student group that is focused on building a rocket which goes to the Kármán line. So, there are a bunch of rocket groups from universities that are targeting that. I think there's probably about like 10 or 12 of them. So, yeah, we'll see which group can get there first.
After we receive confirmation from Mission Control, first of SECO, and stage separation.
Yeah, Astra, the rocket group that I'm a part of, we're also building.
Entering burnout.
We're building our
detect.
sounding rocket out of carbon fiber, which is similar to how Electron is building their rocket. We're not going to be having liquid oxygen inside it, so it's not going to quite have the same thermal things, but in terms of design strategy and construction, there are some similarities between the Electron vehicle and ours. And also, I just think the electric pump engine is just totally cool. Like, what an innovative idea to simplify the whole manufacture process. Oh, you're in Germany too. Are you from North America as well? I come from Canada.
And great news there from Mission Control with a successful SECO. The kick stage is now separated ahead of payload deployment, which is set to take place in the next 45 minutes or so. Due to the innovative payload design intended to keep Electron lean.
Okay, so it looks like they just got the payload into the orbit that they wanted. So now they're just going to be going into basically a coast phase, which will last for, they said 45 minutes, I think. Basically, the reason for this is that they are in an elliptical orbit right now. So they're right now they're at periapsis, and they're going to go all the way up until they reach apoapsis. So that's going to take them about 45 minutes, which is half an orbit, and then they're going to circularize once they get up to the high point in their orbit. Yeah, this is a kind of a cool animation, I guess. So yeah, basically, the reason why they do that, like a question might come up, like why don't they just circularize immediately with the launch vehicle? Like you could just launch yourself into an orbit where essentially when you're just finishing your burn, you'll be in a circular orbit. So why do they go through this whole kick phase process? And there can be a couple reasons why they choose to do this. The first one is that sometimes the rocket itself doesn't actually have the energy to get itself into that high circular orbit, which I think is the case for the Electron here, because it's going up to about 500 kilometers, this satellite, and that's a bit higher than its normal altitude that it likes to launch satellites into. So that's why they would choose to go into kind of an elliptical orbit, and then they let the Madame Curie engine take it all the way up to the final orbit. Another reason for doing this is actually having to do with like payload security and stuff. So sometimes it makes more sense to put your vehicle into this elliptical orbit and kind of have it park there for a little bit and make sure everything's okay and everything is working properly, and then you do your final circularization burn. So yeah, SpaceX does it that way a lot. They don't have an upper stage, a kick stage. They just do everything with their second stage part when they do that kind of a thing. One thing that's maybe not so commonly known about rockets is that they're really kind of imprecise in a way. So they don't really, like the big rocket, like the big booster with the 9 Rutherford engines, and then the upper stage with the big, huge Rutherford vacuum optimized engine. It's not a very precise vehicle. So, if it shuts down like a quarter of a second too early or a quarter of a second too late, that's like a huge difference in where the orbit is. So that's the other problem, is that if you really want to have a precise orbital insertion, sometimes using the big rocket vehicle is not really the best way to do that. And that's another reason why you might want to go into kind of an elliptical parking orbit, where you're like, okay, which orbit are we in, and what exactly do we have to calculate to do the final insertion burn. So it lets the onboard systems kind of figure out where they are and make those fine-tuning adjustments. Yeah, so that's kind of the idea behind it. Anyways, if you guys have any questions, feel free to ask. We can stay online for a little bit longer. Otherwise, I think that sticking around for 45 minutes before it does its final orbital insertion might be a bit not interesting for a live stream. But yeah, if you guys have questions, I'll stay on to answer. Otherwise, we'll probably just end the live cast here. So the summary here is that Electron had another successful launch of this Black Sky, of these two Black Sky satellites. So we look forward to the expanding constellation that Black Sky is building, and I expect that they'll continue launching missions with Electron. They're also using two other vehicles. They're using the Falcon 9. They often use the rideshare program with the Starlink satellites, and they have also used the Indian launcher, the PSLV, and they're planning to also use the SSLV, which is a new launcher that ISRO is developing, which should be an interesting one to watch as well. So that's kind of the future of Black Sky. As for Electron, stay tuned with what they're doing in the near future, because they're actually going to try and do a full recovery of the first stage of the vehicle pretty soon, which is hopefully going to help them become more competitive in the aerospace industry. Because right now they're kind of getting outcompeted by Astra, which is not the group I'm part of, not the student group I'm part of, but the company Astra. They are designing vehicles now which can launch satellites in kind of the same payload capacity as Electron, but for $2.5 million, which is like a third of the price of an Electron. Electrons are about $7.5 million. So because of that, I think they're kind of being pushed into trying to develop reusability in order to compete with companies like that. So really looking forward to seeing what that will create and whether or not Electron can be successful in recovering this booster. It's always exciting to see multiple space companies that are fighting for access to contracts and stuff in the industry, because this is what drives innovation, and this is what causes there to be new ideas and new ways to try and get the job done, which is getting satellites into orbit. And that's kind of an exciting time to be an engineer, because you get to participate in that activity. And so yeah, we're looking forward to participating in that in the future, of course. And we're doing our part to kind of start by trying to develop technology that will take a rocket to the Kármán line. So yeah, looking forward to that. Anyways, thanks guys for joining and checking out the Electron launch, and we look forward to seeing you guys in the future. And remember to expand your horizons.